So we can calculate, the R squared. Um, it's going to be almost identical to what we were doing when we had one variable. It's just that now remember, it's the percent of the variation that we're explaining in the dependent variable from our regression. And our regression now includes multiple dependent variables. So if we think about the sum of those squares residuals now, our predictions include all of our independent variables. So however many X variables we've included on the right-hand side. So here's kind of like the proportion of variation we can explain. We still have the total kind of variation that exists in the data. And then we can also think about this from a different standpoint, which is what can't we explain? And what we can explain is going to be the difference between the actual Y values and our predictions, or our errors, right? Errors squared. So we've got some of the squared errors. This is what our independent variables can't explain. Some of the squared residuals, what we can, and then the total sum of squares is just the total variation that exists. So everything's basically the same. It's just now it's not how much variation does one variable explain, how much do all of our independent variables explain. Okay. So one thing you might be interested in, okay, maybe I have a relatively low R squared. So maybe it's like 0.1 or 0.15. So I'm not explaining a lot of the variation, but it doesn't necessarily mean that the variables that I'm using to make my predictions aren't important, right? Maybe my regression model is still, the variables I've included in it are good ones to use. Yes, hopefully I can go out and find more data so I can explain more of the variation and why, but maybe the ones I'm using are good as well. So I'm going to put these up here. I'm not going to make you do this by hand. I'll show you where these things exist in Excel, but we're going to have our mean square roots of our regression. This is going to be the sum of our squared residuals divided by the number of independent variables that we're including. So you can kind of think about it here. This is going to be what I can explain, sorry, I'm kind of slurring my words, what I can explain using my regression model, like using my predictions. However, if I just start throwing tons of variables, I can always increase my R squared, right? Even if I'm trying to predict income and I add someone's height, well, their height might, influence some of their behaviors. And so maybe that leads to different levels of income. So if I just start including more variables, I can always get a higher R squared, but I'm kind of cheating. If I just put like 1,000 variables in there, right? Some of them are going to stick, right? So kind of what this does is it like scales, okay, yeah, we're explaining this much of the variation, but we've included this many variables, right? We've included 1,000, right? So it's going to kind of scale that down. And then kind of the mean of our squared errors, this is going to be what we can explain, divided by kind of our total number of observations minus our number of independent variables minus 1. Once again, we're not really going to use these a lot because Excel does this work for us and it spits out our F statistic. And then it's just a matter of how do we use this F statistic to make decisions about whether or not our regression model was significant. So when we say is the regression model significant, I did a 2 variable example here. It would just get more complicated if you added 3 or 4 variables. But here I'm going to start out assuming that both of these coefficients associated with the 2 variables I included in my regression are equal to 0. So I used beta here. You might see that in regression models using beta instead of B. It's just the kind of the Greek notation. So I'm trying to kind of show you a little bit of both. And this is a small typo, so glad I'm catching this. I think I just copy pasted and forgot to update it. So my alternative hypothesis is that one of these is not equal to 0. So something that I've included in this regression has some effect, right? It has some relationship with Y that's something other than 0. And then, if we can find evidence that supports the alternative and goes against the null enough, we say, okay, I can reject that both of these coefficients are 0, or essentially what we're assuming is that the model explains nothing. So if we can reject that, we're saying our regression model explains a significant amount of the variation in Y. Okay. So, if I'm thinking about an F statistic, it's going to be very similar to what we were doing with other distributions. Let me see here. I gotta flip this. There we go. So the F distribution has a longer right tail. It's not symmetrical. So it's going to look something like this. But ultimately, we're going to do hypothesis testing a very similar way. And just like the student T distributions, the F distributions are going to depend on some type of degrees of freedom, but we're not going to have to choose which one. Excel will do that for us. Dive into those topics more if this is a more complicated stats course. Excuse me. But it's still the same idea. I can find critical values that give me a desired alpha in the tail, right? And, I would calculate my F statistic. If it's in that rejection region, I can reject. Notice its p-value would be less than alpha. So all the same principles apply. It's just that we're using a different distribution. And the reason why, if we think about what we're doing, we're testing the model's significance. Well, I'm always going to know that R squared is always going to be positive, right? At the very worst, it could ever be is 0. So I can never see negative R squared. I can never explain less than 0 of the percent of the variation in the y variable. So we always know that we're going to be looking at kind of the positive values, which is why our F statistic, our critical values are always going to be positive, right? We're looking at the right-hand side there. Okay. So kind of similar to our student T distributions, although it has 2 degrees of freedom instead of just 1, we're not going to kind of work with F tables, or I'm not going to make you do any of this. All we're going to need to know are those same rules that apply from previous hypothesis testing, which is we reject if the p-value is less than alpha, or if our F statistic, our test statistic, is greater than our critical value. Okay. So here's non-Excel output. I'll then show you what it looks like in Excel, but notice, okay, here's my F statistic. It even tells me my degrees of freedom here. So 44.23. Probability that I see that F statistic or anything greater, or essentially it's telling me there the p-value. Right? So my p-value is basically 0. So I think I was trying to predict wages using IQ, age, and experience in this regression. So these 3 variables, right, this model that I'm trying to use to explain the variation that exists in wage, I would say, is significant at any conventional level, right? My model is statistically significant at any conventional level in terms of explaining the variation that exists in wages or making predictions for wages. Okay, so pretty high F statistic leads to a pretty low p-value. So, any level of conventional significance, we can reject the null. Remember, the null being that none of the variables have any effect. Okay. The next thing that we'll kind of work through, I'll relate this to the crime example, kind of jump the gun over a little bit already. But let's say I run this regression and I find that when counties or cities spend more on their police force, that the slope coefficient's actually positive and that they see more crime. Well, that's probably because they were spending more money because other conditions were bad, but we're not controlling for those, right? So, if we include the unemployment rate, now the interpretation is $1 more spent on my police force holding constant the unemployment rate of the area. Well, that's a lot more powerful of a statement. Maybe then the sign would actually flip. So as I add in more regressions, these slope coefficients can change because I'm now controlling for more things. I'm holding more things constant. Same kind of idea with smoking and birth weight. If you look at data, yes, the effect of smoking while pregnant is negative on birth weights. But, and I think I put positive here and it's negative, clearly. But even though I find it's negative, could it be positive? So if you look at the correlation of mothers who smoke while pregnant, it's also highly correlated with things like socioeconomic status, education level, like all these things that might also lead to changes in the birth weight. So if we don't control for those things, we might find a really strong negative effect here, when in fact, yeah, it's a negative effect, but not near as large. Right? So what is this going to look like? So correlation is not causation. So the problem, if we omit important variables, so this is where if I just use a simple linear regression instead of using multiple linear regression, I'm not controlling for these other things z, which might be causing both x and y to change. So maybe it isn't that x is causing y to change, but that some outside factor is causing both x and y to change. So, got an example here. So like, for example, if I looked at the correlation of autism and organic food sales, if I run this regression with this data, I'm going to find that there's a positive effect. I don't think that organic food sales are causing autism rates. It's likely an outside factor, which is driving both of these go up. Maybe an increased focus on health in all areas. So people are buying more organic food, but they're also being more attentive to their children's health and diagnosing autism earlier. And so maybe there's this outside factor causing both of them. Also the old stupid cartoon I always like that said this. So the one I started the class off with some statistics, how to lie with statistics or something. And this was if you run a regression, you'll always find a positive slope coefficient between um, drowning deaths and ice cream sales. But right, drowning ice cream sales aren't causing drowning deaths. It's temperature, right? This other thing, Z, we're not factoring. So I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe, right? Because, maybe it wasn't that taking the class helped me have this realization. Maybe it was that I was more likely to take the class because I was intelligent and it was my intelligence that led me to be able to figure this out. So kind of a stupid little example. Now, I won't dive into this because I'm not going to make you guys kind of work through all this, but basically you can prove that if you run a simple linear regression, just including one variable X, and you omit an important variable, another variable X2, that you're always going to find that your slope coefficient has the true effect, right? But also this bias, this additional component, right? So we're say our estimate is going to be biased there, right? So I've got kind of this example to kind of run through what this looks like. So here I've got being an athlete and its predictions on your GPA. And then I say, okay, well, what if I include just one more variable, which is that person's SAT score? Because, admissions departments may be a little bit more lax on student athletes than non-student athletes. And so maybe it's not that being an athlete causes you to have a lower GPA. Maybe it's that, athletes tend to have lower SAT scores coming in. Or, maybe the effect of being an athlete, if I could hold constant the person's intelligence level, maybe it teaches things like time management. So maybe it actually has a positive effect. Okay. So you can look at these results, and I've got this in Excel. So I'm just going to actually jump over to Excel in this omitted variable tab, and you can kind of see all these tables are what I just copied them into slides there. So we'll kind of reproduce them. So I've got GPA, SAT scores, and whether or not they're a student athlete. So I'm going to go up here. First thing I'm going to do is run a regression where I'm looking at my Y variable is college GPA. My X variable is whether or not they're an athlete. So select that, Control Shift, Command Shift on a Mac. I've selected my labels, hit OK. Zoom in so I can see what I'm doing. So it looks like there's a negative effect and the p-value is basically zero. So I can reject the null that there's no effect on GPAs for being a student athlete at very high levels, right? So e to the -9, remember, move that decimal 9 places to the left. This is basically a p-value of 0. So I can easily reject the null. So I found a pretty strong negative effect, but I then go back and say, well, look, I know that, admissions standards might be different, especially at these like major D1 universities. So I'm going to go back to my data analysis regression. And instead of just selecting athlete, I'm going to select two of these variables, right? SAT and if they're an athlete. So Command Shift on the Mac, Control Shift on PC, hit OK. Now when I get this regression output, I can see here that, okay, now the interpretation of that athlete, so the unit change is kind of weird here because it's just, are you an athlete? 1, 0 if you're not. So going from not being a student athlete to being a student athlete predicts that your GPA will be about 0.05 points lower, holding constant the person's SAT score. So we went from a scenario where it looked like being a student athlete actually decreased your GPA by 0.28 and was highly significant, to now it only reduces it by 0.05 once I hold constant the person's SAT score. And I can't even say that being a student athlete has any effect, right, at any of our conventional levels because our p-value isn't going to be less than any of our alphas. Okay. So what's another thing we can do? So let's go up here. I don't just have to include two variables. I can include a bunch. So here for my X variables, I'm going to select everything I've got here, right? Except for this SAT squared. We're not going to do anything with that. So hit OK. Zoom in so we can see what I'm doing here. So now the interpretation of my student athlete variable, if I include all of these other variables, is holding constant the SAT score, this verbal math score, their high school rank, whether they were female, their kind of demographic controls, their total credit hours, their high school size. So two students where all those things are exactly the same, but one of them is a student athlete, they would actually expect that their GPA would be about 0.17 points higher. And it is now, once again, e to the negative fifth. So this p-value is basically zero. It's significant. But now the opposite direction, right? Now we can say there's a statistically significant positive effect from being a student athlete. So you can kind of see if you have important other variables that are important and you're omitting them, from very simple regressions, these aren't very reliable coefficients, right? In fact, you can kind of see a lot of these are highly significant, right? We should have been including them. And you'll notice as we add in more variables, what's happening to our R squared. So originally, the proportion of variation we explained was 0.008 or 0.8%. So being a, whether or not your student athlete doesn't explain much of the variation in GPAs. SAT score, once we included that, our R squared should be, our R squared shot up a lot, right? This SAT variable looks like it's really good at explaining a lot of the variation in GPA, about what, 0.16, right? Because being a student athlete didn't explain much. Then if we include all of them, now we're up to about 0.3. So we're getting close to explaining a third of the variation that exists in GPA. There's likely a lot of other important omitted variables that we still don't have, but these results are a little bit more reliable than when we were just running a simple linear regression. Okay. Once again, the F statistic we talked about earlier, I can say here, is this model, is this a good statistically significant model explaining variation in GPAs? Well, the F statistic is huge. The p-value is basically zero. So yes, right? I can reject that this model explains no variation. Right? And then even here, I could reject even just including SAT and athlete. Hell, even just including athlete, I can kind of reject. Okay. Okay, so let me think if there's anything else I want to say here before we go back. Slide. So I've got everything that I just did there, kind of, slightly different format, but this is the results that we saw from Excel. But we can see once you start including these important omitted variables, things can change quite a bit, right? Our coefficients can change signs, they can change whether or not they're significant or not. So there was some Excel work done here. I'll post an additional video where I work through a little bit more. Actually, I'll just cut it out of this one. So just to kind of show you a quick and easy way of doing this. So on the Excel homework, one thing that I might ask you to do is come up with rejection decisions for each one of these variables. So we'll skip the intercept for right now.